So this is lecture number 15, E211, analog circuit design. So unfortunately yesterday, because of some problem, I could not complete the lecture number 14, where we're talking about the amplifier transfer function. But before that, we studied about high frequency model. So high frequency of model can be used to find out the complete transfer function. And we discussed about the single transistor with some load. Let's assume that the same thing is there, and the low frequency gain is already found out. It's minus gm times ro1. Now let's move to the next part, where you're going to add so many capacitances. Like there are two overlap capacitances, cgd cgs, and other than that csd and cdb are there. So those are the plate capacitance, and those things are there. So you need to add those things. Once you have those things, and those are creating some connection, all these capacitance and all these things needs to be taken into account, and you have to find out where are the poles. So here you can see that we have added all the parasitic capacitances at high frequency, and we need to find out how many poles are there in the system, as we are working at high frequency and there are three dissimilar plates. I can add actually the capacitance in between that thing. So I did it. Now the next part is how many poles are there. So how many poles are depending on the number of capacitances, the effective number of capacitances, and through that capacitance you need to find out how many what are the resistance in shunt with the effective capacitance. But before that, we need to move further, and we need to make sure that it's only, like, we also learn that it has to be only one dominant single pole in the system. But let's see whether our system has how many poles are there. So if this is a current as a load, and there is a transistor whose name is M1, two resistances who are biasing gate potential with coupling capacitor, we are doing this. And when we are doing this at high frequency, this is short circuit, by the way, because this is a big capacitor, so it will be shorted. And notably, there is one resistance which is 50 ohm, will be in series of this function generator. By the way, this is a function generator. Now I have added some of the parasitic capacitances. This we are calling it CGD, this we are calling CGS, and this we are calling CSD plus CDB. Right? This is junction capacitance, and this is source to drain capacitance, if there is any. And maybe like addition of that, there might be some load capacitor also. Let's call the whole function as C2, where C2 is nothing but CSD plus CDB plus CL. Now I know that the system looks little bit complicated when it's not look like a pi model. If you draw that, you can see that there is a capacitance which is here. CGD is between gate to drain, and from gate to drain there is a negative amplification whose value is minus gm1 times ro1. So from this point to this point there is a gain, and in shunt with that there is one element. So in that case we can apply a Miller theorem, and we can decompose this capacitor both sides. You can keep one capacitor here and one capacitor here, let's call this one as CGD1, and let's call this one as CGD2. When it's coming here, we remember that the impedance like CGD1 and CGD2 will follow the equation, which is this one, where Z will be replaced with 1 by j omega c, 1 by j omega cs, and AV is minus gm rho1. However, like you can replace minus gm1 rho1, but I am telling you one more thing. Like this is an assumption, but the assumption will work for the technique which we are working on, that says that amplifier gain or the transistor gain, even if it's like gmro1 is in the range of 18 to 20 volt per volt. I'm saying that that gain is also, we are going to consider that one as also infinity, just for simplicity, so that you can have the better picture. So if gain from here to here is infinity, then as we know that the input side, that is infinite impedance, and other side it's same as what we are seeing here. So CGD will be here. So at the input side, zero impedance, and because of zero impedance you need to keep the infinite capacitor. So that is going to give you such things, right? So if that is the case, let's redraw this, where there are only two capacitors. So now there are only two capacitors. One capacitor which is CGS, one capacitor which is at output. We already agreed that it was C2, where C2 was nothing but CSD plus CDB plus C load. But on top of that, it's also one more capacitor which came from here, which got decomposed in Miller theorem. So CGD will be added in this one. So CGD plus C2, that will be at the output, right? So there are effectively there are two capacitors. So in this system there will be two poles, right? So there are two capacitors, means two poles. Let's find out where the locations are. So the locations are as follows. You need to replace each of the capacitor with a known Thevenin voltage, and you need to find out what is the available resistance at these two nodes, right? So let's start from here. So let's call this one as first pole omega p1, that will be equal to minus 1 by the resistance seen at this node. Let's call this node x and this node y. So rx times cgs. Now if I need to find out rx, I need to replace this with a known voltage source, and I need to see that all other voltages are going to zero, and in the case of VDD it's already zero because it's an AC ground. Note that I'm not drawing the small signal model. However, you need to draw the small signal model and you need to solve this. So maybe you can see that it looks like this one. So at the input side, there are two resistances, R1 and R2. So this is R2, which is already here, but R1 will also go to ground. By there, this is VDD, but this is AC ground right now. What we are doing is AC analysis, so all DC goes to zero. And here there is a 50 ohm and there is Vin, but Vin will go to, it will be shorted because we're following the Thevenin. And I'm interested in finding out the resistance over here. Similarly, for here it was C2 plus CGD, and at output there is impedance of this current which is infinite. Let's call it R current, which is equal to infinity by the way. So I need to find out the node resistance at this particular node. So in that case, when I'm replacing this, I'm going to see three resistances. Let's call this one as X node, this one as Y node. So resistance at X node is equal to 50 ohm in shunt with R2 in shunt with R1. Notably, R2 and R1 are very big quantity, so 50 ohm is going to be the winning quantity. So in that case, the first pole location is equal to minus 1 by 50 times CGS. So you can highlight this, you can keep it with you. And second pole, you need to find out at this node, but the capacitor value is already known to us, C2 plus CGD. So at this node, I'm going to see following things. By the way, this is VGS is 0, so this current is 0. This is already known to us. At this point, if you are looking at drain, it's R0 only which is going to be seen, but R0 in shunt with R current, where R current is actually infinity. So the winning quantity is R0. So there are two poles now. So one pole is at minus 1 by 50 times CGS, and another pole is minus 1 by C2 plus CGD times R0. So you can see here that the first pole which we are seeing, actually it's not a first pole because R0 is in range of kilo ohms and this is 50 ohm, and like CGS might be smaller than C2 plus CGD. However, taking this multiplication thing, omega P2 denominator is the winning quantity, it's bigger one. So if you're looking at that, omega P2 is lower than omega P1 because of this 50 ohm. So let's keep this thing here, that omega P2 is less than omega P1. So we are not going to call this one as omega P1 in that case. Let's call this one as omega P2 and let's call this one as omega P1, right, because of this 50 ohm. Notably, if you can see that this 50 ohm is a very small quantity, we also consider it's as low as 0, or we consider that one as low resistance. So in that case, this frequency is going to be available at infinity or very high frequency, or you can also say that it will be much higher than the UGBW. So if you draw the Bode plot, so magnitude response is going to give you, so let's, this is omega P2 and this is omega P1, where omega P1 is nothing but 1 by, so now it's mod, so it's 1 by CG D plus C2 times RO, and here this is equal to 1 by 50 times CGS, which is available at very high frequency. This is UGBW, and this will be gain. Notably, gain is already known to us, it's equal to GM times RO, which is in the range of 18 to 20 volt per volt. And after omega P1, it's moving ahead, and you can have the UGBW or the unity gain bandwidth, right? So as there is only one pole before UGBW, this system is inherently single pole dominant system. Yeah, this is one thing. And second thing is, because of single pole, if you draw the phase plot, it's going from 0 to minus 90. Maybe from here you can observe that it goes So this is minus 135 and this is going minus 180. So this is minus 180 line. So with respect to frequency. So at UGBW, if you are measuring the phase is actually minus 90 at UGBW. Phase equal to minus 90, and therefore phase margin is equal to phase at UGW plus 180 degree. So this is going to give me plus 90 degree. So because of plus 90 degree, this system is stable. There is no problem. That was also known to us that it's a single pole dominant system, so there is no problem in terms of stability because it's not going to give us any problem. So that is also the reason that I'm saying that the system has two poles. However, because of this function generator's 50 ohm impedance, actually it's exhibit as single pole dominant system. And if you look at that, bandwidth is equal to dominant pole location also. So if it is 3 dB bandwidth, 3 dB bandwidth is equal to the first pole, which is already known to us. This is because of this one, not because of this one. So that one is, or you can say that 3 dB bandwidth we can write down as minus 1 by RO times C2 plus CGD, where C2 is CSD plus CL, right? So this is what is actually about the single stage common source amplifier. Now let's move further. So this illustration is also like it's a repetition of what we have done, but if you need to find out the gain, it's minus GMRO, which is also the intrinsic gain of the a transistor. Bandwidth means 3 dB bandwidth is exactly equal to minus 1 by C2 plus CGD times R0, right? If you want to have it in hertz, you can add 2 pi, so then it becomes in hertz. Gain bandwidth, so gain is already known to us, minus will become plus, so GM times RO times the bandwidth. So gain is GMRO and bandwidth is already known to us, 2 pi C2 plus CGD times RO. So this becomes GM divided by 2 pi C2 plus CGD. So that's the gain bandwidth or unity gain bandwidth, you can say that, right? So it's in hertz because of this 2 pi. So these are the already all the answers which we have found out. Now we also talked about the magnitude response, phase response, and we can comment on the stability. So for such a system, it's always stable because it's only single pole dominant system. That is the reason, right? Now I'm asking you to find out following things. It's one of the illustration where you need to find out the ZX. So ZX has two things. One is capacitor and one is actually capacitor and one is a resistance, right? So let's assume that this is a function generator which is connected over here, 50 ohm. So while doing this is shorted and I need to find out what is the impedance over here. So it's impedance wise CGS in shunt with RS, right? That's the, so that's the impedance seen over here at ZX. Similarly, Z at V out is equal to CDB in shunt with, if you're looking upside, it's RD, and if you're looking at downside, it's RO1. However, looking at the CGD, which is actually decomposed over here, while considering the fact that M1 gain is infinity, then this is CDB plus CGD. By the way, there is one small mistake. By the CSD is very small number, by the way. So you can drop that and you can only use CDB rather than CSD. CSD is very small. Yeah. So as shown over here, it's only CDB which can be taken into account because CSD is very low. Anyway, so but it doesn't matter. The only thing is it's a whole theory that like how you are connecting these capacitors, how you are decomposing that, and how you are getting the values. So now for such thing, I need to find out the AV, which is small signal AC gain or very low frequency gain, where the capacitors are not there. So in the absence of capacitance, you can see that it's minus GM1 times RD in shunt with RO1. That's the AV. I know that find the pole locations. So there are actually two capacitors, effective capacitors. One is CGS and one is CDB plus CGD. However, because of this 50 ohm, the second pole is acting like this, RS times CGS, where RS is actually 50 ohm. And looking at first pole, it's minus 1 by CDB plus CGD. There might be some load also, then load will be added over here. So looking at resistance over at this node, it's RD in shunt with RO1. So these are the two poles. So while writing the transfer function, it looks like AV divided by S by omega P1 plus 1 and S by omega P2 plus 1. So if this is 50 ohm, then it's available at very high frequency, and overall the system is actually single pole dominant system because of this 50 ohm contribution from the source. However, if this is connected from another stage of amplifier, then this will not be the case, and then you will observe there are two poles, and there might be the case that both the poles are within UGBW, or it depends on where you're keeping those. Okay, so now this is the small signal model, and like it has been solved thoroughly the way we have done it, and this is the whole transfer function. By the way, these things has been taken from Razavi. Now let's say you have the cascading of two stages, and you need to find out the total number of poles and gain and all these things. So first of all, if you need to find out the gain, it's gain contributed by the first stage multiplied by the gain contributed by second stage. So A1 times A2, where A1 is first stage gain and A2 is second stage gain. So multiplication of these two is going to give you the gain, right? So in that case, you can write down it's minus, let's assume that both are identical, or okay, as given in here, it's GM1 times RD in shunt with RO1. This becomes plus, by the way, because of 2 minus, times GM2 times RD2 in shunt with RO2. That's the AV. Now, if this is already known to you, let's draw the small signal model for the entire system. In that case, for M1, this becomes GM VGS1, GM1 VGS1. This side, it's 50 ohm and the function generator. And other than that, this is, by the way, RO1. And at the output of the first stage, RD is kept. So let's keep RD, and it's grounded. This is first stage output. I'm not connecting right now any capacitors. Capacitors can be added on the later stage. and the second stage looks like this one. So GM2, VGS2 and RO2, and this side it's RD2, right? So this is V out, this is V out 1. So this is output at the first stage and this is output at the second stage, or both the stages. Now let's add all the capacitors. So we already know that there is a capacitor CGS 1, there is one more capacitor CGD 1, and there is one capacitor CDB 1. Similarly, at this side it's CGS 2, CGD 2, and here you are going to observe one capacitor called CDB 2. So now, like as we like the small signal model only, and it has to be in pi model, then we don't like to have these capacitors. Notably, these capacitors are in shunt with these two transistors whose gain is GMRO. However, we assume that GMRO is big enough that it's going to give you the quantity which is infinity. Let's assume that. If that is the case, then when you are decomposing this capacitor at the input side, there is no capacitor is going to be reflected, and at the output side full capacitor is going to be reflected, whichever is connected between input and output. So in that case, let's remove this one. At input side, means at this side there is no capacitor. However, at the output side you are going to have that capacitor because of Miller. Similarly, the CGD2 is going to be reflected at the output side with the fact that the gain of a transistor is infinity, or GMRO. So now you can see here effectively there are three capacitances I can see. One is this one is the combination of these three, which is CDB1 plus CGS2 plus CGD1. So this is second number capacitor, and the third one is CGD2 plus CDB2. That's the capacitor available over here. On top of there might be the load capacitor, and here it's CGS1. So if we know that there are three capacitors, we need to find out the three pole locations. Let's find out three pole locations. Let's start from the input side. So in that case, the pole location or the resistance seen at this node is going to be equal to 50 ohm only, because at that time you are going to short this and the rest of the things are no more available. So uh, it's only 50 ohm. So let's write down one of the pole location is minus 1 by 50 times CGS1. Another pole is available at the middle. So we need to find out the resistance at this node. At this node, we are going to see three things. While doing this, by the way, this VGS is 0, so this is not there. Or you can directly see from here that at this node you are. So there are three branches I can see. One going in this direction, or the input of the transistor. One is going upside and one is going down. When upside, I am seeing RD with the fact that VDD is 0, or it's an AC ground. And this side, on looking at drain, it's RO1. So RD in shunt with RO1 in shunt with infinity. And that is what you can see here. RO1 in shunt with RD in shunt with infinity. That's the resistance you are seeing at this node. Notably, at that time VGS equal to 0. So second pole you can write down minus 1 by RO1 in shunt with RD times CDB1 plus CGS2 plus CGD1. This is another pole. Now looking at the third pole, which is available at CGD2, 2 plus CdB2, you can write down the resistance at this node, which is going to be equal to RO2 in shunt with RD2, because it's also again easy. You can see here at two branches are there. One is RD2 on top side and one is RO2, which is going at the drain of the drain of a transistor. So in that case, it's RO2 in shunt with RD2 times CGD2 plus CDB2. So there are three pole locations we know, but now we need to find out which pole is actually the higher one. So if you're looking at to that, notably, or first I will go to this 50 ohm thing. So because of 50 ohm, this whole thing may go to much higher than UGBW. So this is available much higher than UGBW, and you cannot predict which one is higher. It's all depending on the value of capacitances, value of RO, and in principle generally this has to be first pole and this has to be second pole and this one has to be third pole. However, if there is some designer who is keeping the first stage much bigger than second stage, when I'm saying much bigger than means W by L of the first stage is uh, bigger, or it's badly designed, then omega p1 becomes omega p2 and omega p2 becomes omega p1. So it's all depending on the design part, and it's all depending on how you are designing the things. So in that case, we cannot predict at the moment. However, it's expected to keep omega p1 as what I have written and omega p2 as I have written, and it has to be like that. Otherwise, it's a bad design. Otherwise, it it can create a problem. Now let's move further and let's talk about one fact that we know two kinds of things: pole frequency and zero frequency. So what is pole frequency? So the pole frequency is the one which has to be seen in the transfer function. So whenever the transfer function becomes infinity, so you can say that the frequency at which at the pole frequency this becomes infinity, whereas zero frequency is the one where transfer function becomes zero at that particular frequency in radian per second or in hertz. So it depends how you are doing the analysis, but generally it's like frequency, pole or zero frequency, where pole frequency is the one which is going to give you transfer function as infinity, and zero frequency is one which is going to give you zero, right? Generally poles are so if g omega versus real axis, then poles are denoted with cross and zeros are denoted with zero, circle kind of thing, right? So this is already known fact to us. If we use that, and if you again like formulated in terms of definition, the pole frequency is the frequency where the transfer function becomes infinity, and zero frequency is the frequency where the transfer function becomes, okay, this is a mistake over here, it has to be zero. So let's use that. So what I'm saying, if I need to find out zero, zero is the one where V out by V in at this frequency it becomes zero. So I can say that V out is zero, right? For no matter what value of V in you have, you just say that V out equal to zero. And if that is the fact, let's make a technique in which, on top of finding out poles, AV means the small signal AC gain and other things, let's find out the zero. So in that case, we need to connect V out to ground potential. Notably, this is what we are doing just to find out zero. In reality, we are not doing it. We are doing it on paper only, right? So if this is the case, you can take out the whole transistor out and you can connect V out to 0 with all the available capacitors. Oh, by the way, this has to be CDB. So if you are doing this and if you are moving further, you can see that there are two paths. One is this side, one is this side. Let's call this is first current as I1, second current as I2, and this one becomes 0 when I1 equal to minus I2 or vice versa, right? I1 equal to maybe I and I2 equal to minus I or vice versa. Then this is possible, right? So that like the current is not moving this way but it's going this way. So it's going this way. Then this is possible. This is one fact, and that is what shown over here. Now, notably, M1 is in saturation. This is one fact already known to us. And this is a low resistance path where it's a short circuit, right? This is another truth. And third one is I1 is equal to I and I2 is equal to minus I. So these are three facts already known to us. If these three facts are known to us, what we can say that is going from this point, which is X, and let's call this one as Y point. Actually, okay, rather than calling it this one, this is, let's call this one as V1 point, and this is already ground or 0 volt, right? So from going from here to here, the current is actually GM times VGS. If you look at the current flowing through the M1, it's actually GM times VGS, where gate potential is connected to V1 and Vs is already 0. So that's the current flowing through this one, right? And the current flowing through this one is nothing but V1 minus 0 divided by 1 divided by SCGD. So this is the current I1 is nothing but V1 times SCGD, and the current which was flowing in negative direction, but if you look at the I2, it's in the same direction. So this is becomes GM times V1. That's the equation. So this is I2, by the way, and I1 and I2 both are same and opposite. So this particular equation you can have. So if this is the equation available with you, then you can say that SCGD equal to GM. Now you can replace this with omega z, where omega z is nothing but a frequency which is referring to 0. So in that case, you can have omega z equal to GM by CGD. Right? If you are taking the, we are talking only about the real frequencies. So in the real frequency, we are going to have GM by CGD in radian per second. However, if you are interested in hertz, it's 2 pi CGD, and you can see the dimensions. The dimensions wise, it's all are like matching the one which we require, and notably it's at plus side. It's not at minus side, it's at plus side. So that's why this is also known as right hand side 0. Let's call this one RHZ, which signifies that it is available at right hand side, and this 0 is right hand side. Now if I am interested to write down the complete transfer function, which has the gain, which has the pole locations and 0 location, because that is the main thing. And I forgot to tell you one thing, that the way we define the pole location, that we need to see how many capacitors, effective capacitors are in your circuit, that many number of poles will be there. Similar to that, if there is a path from input to output through a frequency element like capacitor or inductor, you may have zero. Or you can say that if there is a capacitor between input to output, so in that case there is transmission of zero, or zero frequency will be there. So uh, in this case, let's start with writing the transfer function, where transfer function looks like this one. So you can see here I have written basically three things. One is uh, small signal gain, two poles and one zero. Two poles because this omega, this CGD is reflected over here and one is reflected over here. But we know that the capacitor, when it's reflected over here, it depending on the gain of the gain element. Here the gain element is transistor, and we assume that the gain of M1, which is GM times RO, is much higher than like it's actually infinity. So if it is infinity, at the input side there is no capacitor. However, at output side there is a capacitor, and it will remove this part. So it will be CDB plus CGD. So it's reflected over here. So effectively there are two capacitors. So there will be two poles. One of the pole is available at minus 1 by RS times CGS, and at the output side minus 1 by CDB plus CGD times its RO1 in shunt with RD. The second pole. So we know that RS is 50 ohm for coming from function generator. That's why like this is going to be available at much higher than the UGBW. Let's call this one as omega P2. Let's call this one as omega P1. Those things will be fade over here. And as there is a path from input to output through a capacitor, so there is a path from input to output through a capacitor. This is input and this is output. We know that we need to we know that there is a zero frequency. So if there is an input to output path, then this has happened. Otherwise, if there is no path, there is no problem. Like like this case, if this is the circuit, you can see that V out by V in is equal to 1 by 1 plus RCS. However, if there is a circuit like this, it becomes R divided by R plus 1 by CS. That's V out by V in. And that also qualifies the fact that there is a zero availability. So you can see that there is one zero at origin, and there is one more pole. So effectively there is one capacitance, and because of capacitor there is one pole, and because of capacitor going from input to output side, input to output, it's creating a zero frequency. So that fact can be applied over here, where in this particular circuit there is a capacitor between input and output. And notably, when we are doing this, note that the pole were found out by decomposition of the capacitor, or you can say that we have applied Miller theorem. But in this case, we have to come to the zero step where there is no Miller has applied. So in that case, there is a CGD from input to output. So with that fact, there is a capacitor from here to here, and as per our technique, we are connecting this to 0, and we find out the current from both the side. So I know that the current from here it's Gm times V1, and the current from this side it's CGDS times V1. So therefore, replacing Laplace operator with j omega z, where omega z denotes the zero frequency, then it becomes Gm by CGD in radian per second. To make it hertz, you can add 2 pi to make it hertz, right? So writing the full transfer function, where there are three things. One is small signal AC gain, 2 poles and 1 0, and this 0 is at right hand side. It's available at right half plane, and these two are available at left half plane of the S plane. And yeah, but when you are drawing in a magnitude plot, both all will be looking at the positive side, because we are looking at the causal system, or you are looking at the positive frequencies only. So in that case, let's look at the transfer function. It has to be -1, by the way. Sorry, it's a mistake because it's at positive side. So this is the transfer function. When you are drawing the magnitude plot, it might be depending on where the location of 0 is. If it is outside, so this might be one of the possible magnitude response, where this gain is nothing but GMRO. And phase wise, if this is the case, then the its phase margin is actually 90°. But if this one is inside, you can find out maybe on your own that what is the phase margin, right? So you can find out that, right, if this is the case. Okay, so for you, like, I can find out this so that the things will be much more easier for your case. So this is 0, -45 and -90, and when there is zero frequency, this whole thing become reverse. This is happening because at omega equal to 0, the phase offered by this zero frequency is 0°. At infinity, the phase offered by this one is +90°, and at exactly at omega z, it is offering -45°. Sorry, +45°. So by doing this, you can see that this kind of phase plot you are going to have it. So this is phase with respect to frequency. So in that case, by the way, there is no UGBW for infinite, like omega p2 will be acting as your bandwidth, right? So there is no point of phase margin at all, because it's not going to cross before the infinity. But when it's going to touch that, like this, let's assume that it's touching here at higher than, so now UGBW will be lower than, sorry, higher than omega p2 only, because omega z is inside. In that case, it's going to be giving you, in the worst case, or like it will be around +90°. Look at that. The phase margin is equal to +90°, because UGW is much greater than omega p2. and this is also happening because of omega z is inside. But this is one possibility. Omega z might be before before pole also. So then in that case, if that is the case, then the magnitude response will look like this one. So this is gm times rho. Then at omega z, it will start with plus 20 dB per decade. Thereafter, with omega p1, it's 0 dB per decade because minus 20 dB per decade will be added. And thereafter, like at very high frequency, you may have omega p2. Then UGBW will be observed accordingly, right? And effectively, if you look at this zero and pole will uh, cancels each other's phase possibility. And here also, like if you look at the phase margin, it will be plus 90 degree because of this one, right? So because this is going to give you 0 to plus 90 degree and this is going to give you 0 to minus 90 degree, effectively adding both of them is going to give you 0 degree at the end. And like afterwards, you're going to see the phase by omega p2 as 0 to minus 90 degree and the phase margin equal to plus 90 degree. So this is happening all because of where you are keeping the poles, and this is very important as designer to place their poles and zeros at the according position. And notably, this is right hand side 0. So right hand side 0 is actually having uh, having a positive kind of oscillations. So you can see that it's at positive side. So the system is inherently unstable, by the way. If you look at the time domain, this is frequency domain. That's why it's look uh, that's why it looks negative feedback, or all the things are available at positive side. That's why things are fine and your phase margin is much higher than 45 degree. But there is one more fact that this is available at right hand side. And because of right hand side, if you remember previous theory of control, where anything is available at positive side, the time domain wise, it's growing one, or it's oscillating and it's growing. So system is unstable with respect to time. If I'm drawing amplitude with respect to time, so the system which has 0 like this, as by omega z minus 1, you can see that when you are taking in time domain, it's positive side, as an exponential term is growing and growing. It's not going in minus side. So the system is inherently unstable. So with this particular thing, it's an unstable system. However, you need to fix it to stable system using some compensation techniques, which is sometimes people are using Miller compensation, sometimes people are using pole splitting, and there are lots of things are there. People are using nested Miller and lots of things depending on what kind of amplifier and what kind of amplifier topology you are using. However, it needs to be fixed. This is the fact. Otherwise, your amplifier is actually unstable system, and when you're keeping in negative feedback, it will not work and it will keep on growing, and the system will not work the way you want. So it has to be fixed. Maybe rest of the things on common drain and common gate amplifier we are going to talk maybe on the next lecture. So thank you for today.